Am I recording? Am I recording on the computer or am I recording somewhere else? Hopefully I'm recording. Well, I hope I'm recording correctly. All right, so this is a recording for anybody watching this later. I'm going to share my screen. Let's see this screen right here. We are currently working on the Jamboards. I've given two problems on the Jamboards. This first problem here, number 142 from the section. For this one, we have this expression, square root of x squared minus 25. In that format, we want to use secant for our trig substitution. So in particular, x equals 5 secant theta. We have students working on that problem on the first 4 pages. That one's a little spicy. But we have another problem on the next 4 pages that students are working on. And this one is a little different. It involves the expression the square root of 1 minus x squared. When you're subtracting x squared, instead of subtracting from x squared, you see this is subtracting a constant from x squared, whereas this is subtracting x squared from a constant. In this format, the trig substitution that works out is x equals sine theta. So I'm trying to see if they did that here. I think they used u equals sine theta, d theta equals cosine theta. It's a little hard to tell there, and no one else is working. Oh, here we go. Here's another one. X equals sine theta. So if you're watching this later, please go ahead and try those two. I'm going to pause this recording now, and then I'll start recording again when we discuss those two problems. Recording. Okay, I'm resuming the recording. So let's start with, we're going over these now. Let's start with number 142 here. It was the integral of the square root of x squared minus 25 all over x dx. So as we said, we start with x equals 5 times secant of theta. And remember, the reason it's secant is because we recognize any integral involving, well, not any integral, but, you know, if the integral involves the square root of x squared minus a constant, then we might want to use x equals secant theta. The reason I'm saying might is because sometimes you can solve integrals like this just using a regular u substitution. So I haven't really mentioned that yet, but when you're looking at a problem like this out in the wild, you might want to just try u substitution first, because if you can do it that way, that would be a lot easier. If regular u substitution doesn't work, the trig substitution is an alternative. So, all right, so with this substitution, we're going to need to know what dx is. So we're going to need to do the derivative of secant, which we know is secant times tangent. Now, make sure to use a different variable. I'm using theta. Our textbook uses theta. If you don't like using theta, you could use some other variable, like you could use u if you want to, although since this is significantly different from u substitution, I think using u might get confusing. You could use t. T is a common letter for an angle. So, you know, there's other alternatives, but don't use x again. That's a mistake. I made a comment about that for one of the groups. Now that we've got that, we're going to do some substitutions in here. So we're going to get, I'm going to go ahead and square both of these. So we're going to get 25 secant squared theta minus 25 all over. And then our x in the denominator means we also have 5 secant theta down there. Now the dx is going to be replaced by all of this. So I have times 5 secant theta tangent theta d theta. That's my whole new integral. Okie doke. Now, a lot of things cancel out here, which is kind of nice. Right? We have 5 secant theta in both the numerator and the denominator. So all of that is gone. Now, inside that square root, we can factor out a 25, take the square root of 25 to get 5. And so then we can pull that out of our integral. So there's going to be a constant factor of 5 left over from that 25 that was in there. That leaves us with just square root of secant squared theta minus 1 inside there. And then we have just tangent of theta d theta left over out there. Okay. Now we can say, well, let's bring in our trigonometric identity, right? Remember that the whole reason we chose this is because we're going to be we were anticipating arriving at something like this, and then we can take that and apply the trigonometric identity, the Pythagorean identity, or at least one version of it, which is that secant squared minus 1 is tangent squared. Okay. For today, right now I'm not gonna worry about this absolute value of tangent theta and wondering whether we're gonna get a plus or a minus. Generally, you don't actually have to worry about that. It's sort of like a concern that you want to address, but then it turns out it doesn't tend to matter. The only time it matters is well, like I said, I don't want to really get into that right now. So let's not worry about that at the moment. So for now, we will treat this as canceling out directly and giving us tangent of theta times tangent of theta. So we end up with tangent squared, right? And we have to figure out, well, how are we going to integrate tangent squared theta? Well, this is what I was talking to Matthew about earlier. And there's this really handy way to do this, just using that Pythagorean identity again. Before we go any further, I'm just going to check with Isa here on a quiz or exercise sheet. Should we just put plus or minus in front of the answer if it was tangent? No. Let's address that at the end here, because I think if we look at the answer that we get when we're done, we'll find that the negative version is not actually an antiderivative. Let's double check it at the end. Yeah. Yeah. So, okay. So how do we integrate tangent squared? Well, I think getting back to that Pythagorean identity is helpful because if you can replace tangent squared by secant squared minus 1, so basically undoing the same kind of substitution we did over here, right? Going back. Secant squared minus 1, I'd much rather integrate that than tangent squared because secant squared, remember from calc 1, secant squared is the derivative of tangent. And that's on your reference sheet that you're allowed to use during quizzes. So yeah, if I just make that substitution with that identity, then now I can integrate this fairly easily. This is just going to be tangent of theta minus, what am I going to get when I integrate 1? Theta. That's right. This is something that came up a few times for some of you on the quiz I just finished grading. When you're integrating a constant, you have to pay attention to what variable you're integrating with respect to. So like on the quiz, there was a u substitution. You ended up integrating a constant with respect to u, and you're supposed to get u, not x. So that's so in this case, because we're integrating with respect to theta, we should get theta. So now we're here. I can distribute that 5 back through if I want to, but you know, the main thing we have to do now is just figure out how to get this back in terms of x instead of theta. So now, if we want to do that, I think the key idea is we have to go back to this relationship, and it can be helpful to draw a reference triangle just as a visual aid, right? So if we put theta in one corner, we just need to set it up so that rearranging this ever so slightly, we get secant of theta is going to be x over 5. how do I set it up so that secant of theta is x over 5? Well, this would mean that cosine of theta is 5 over x, because secant and cosine are reciprocals of each other. If you ever forget which trig functions are reciprocals of each other, remember it is on the trigonometric identity reference document. So like that's another thing you'll have access to. You can check if you forgot. Just look it up. So cosine, if you remember SOHCAHTOA, cosine is adjacent over hypotenuse. So it should be adjacent is 5 and hypotenuse is x. So then using our regular, Pythagorean identity here, the unknown side that's left over here is going to be, it's going to fall into that place there in the Pythagorean identity. And so that is going to be the square root of x squared minus 25. So I'll label it right here on the triangle. Is everyone comfortable doing the trigonometry here for like placing, like labeling the sides of the triangle correctly according to SOHCAHTOA and then solving for the third unknown side? Is that all, like just doing that Pythagorean stuff fairly? It's been a while, right? Like this is back in 1201 for some of you, or maybe math 1210, or maybe a high school math class. Like it's been a while, I know. So
I have a question.
Go ahead, Ali.
After you do that, does it always go back to like the beginning?
Back to the beginning?
Yeah, like where the problem started. It says x squared minus 25 all in the square root.
Oh, yeah, it does. Yeah, good point. Yeah, this and is always this, right? Whatever expression was in there that you were like, oh, hey, that's the thing that tips me off, that that tells me, oh, I need to do a trig substitution on this problem. Yeah, that expression, that square root expression always shows up, and it's always the same. Yeah. So yes, what we have now is 5 times tangent of theta, which is 5 times opposite over adjacent here. So 5 root x squared minus 25, and then over 5. So I guess the 5s can cancel out. And then for 5 theta, you can't really use, you can't use this trigonometric triangle, reference triangle thing for theta. You just got to go ahead and just solve for theta. So we can just do 5 times arc secant of 5 over x here. And there we go. There's our answer. Export that guy for you. And I think we have time. I think we'll have time to do one more. Might have to kind of work through it a little more quickly. Checking the chat here. We have a question. Did I say x over 5? Oh, yep. No, you were right. It is x over 5. I said 5 over x by mistake. X over 5 is correct. Thank you. Oh, what Isa is saying. I'm not sure what you're saying. You have to figure out, without using a reference triangle, to see what your original square root ended up as. The square root. This ended up as a tangent. Is that what you mean? Oh yeah. No, I think I see you there. So that tangent does end up being that. Yeah, that square root did simplify to tangent. So if you know they're equal to each other already, I guess you can just reverse that. Is that what you're saying? Like that this ended up being equal to this? Yeah. Oh yeah. Very clever. Yeah. Yeah, I don't know. That's awesome. I'm glad to see that connection. Thanks for pointing that out. Let's do the other one. The other one's a little shorter. So 139 here. Integral of 1 over x squared times this square root. And then I put the dx. It has the dx up here, but I like to put the dx over on the side so I can really see my integrand very clearly. I don't know. That's just how I like to do it. So because we have this expression involved here, we can infer that we need x equals sine of theta. It's just one sine of theta this time. So dx is cosine theta d theta. There we go. So now we're going to substitute some things in. Let's see. X is sine, so we're putting sine in for x. That's going to be sine squared. And then we have square root of 1 minus sine squared. And then the dx is times cosine theta d theta. So first of all, let's do something. I'm going to put the cosine theta in the numerator here. And then let's do something with what's inside here. Our Pythagorean identity will tell us that this here is equal to cosine squared. And then we're going to have the square root and the square cancel to cosine to the power 1. Lovely. So now we have a cosine theta in the numerator and the denominator, which cancels out. So now we have 1 over sine squared. Aha! 1 over sine squared. Well, 1 over sine is just the reciprocal of sine. And checking your trig identity reference paper, you can see the reciprocal of sine is cosecant. So this is actually just cosecant squared. And then, this actually works out quite nicely because cosecant squared is the derivative almost the derivative of cotangent. The derivative of cotangent is actually negative cosecant squared. So the antiderivative of cosecant squared is negative cotangent. So and that is on your derivatives and integrals reference document that you're allowed to use. So there we go. So that integral ended up being nice and easy. So now we just need to do the reference triangle thing to see what cotangent is in this context. So let's go back to this again and draw our reference triangle. Okay, if sine of theta is x, since sine is opposite over hypotenuse, I want to do x over 1. Remember that if it's just x, you can, assume there's like a 1, x over 1, right? Equals x. So we do that. And then solving the Pythagorean identity here, this is going to be the square root of 1 minus x squared. So as Ali was pointing out, that is the same as that, right? No surprise. And then now our cotangent is the reciprocal of tangent. So instead of opposite over adjacent, it's going to be adjacent over opposite. So we're going to get the square root of 1 minus x squared all over x with that negative sign, and that's it. That's just like a, what's that on the Scoville scale? That's like maybe a jalapeno. The previous one was a habanero. Do I have that right? Habaneros are spicier than jalapenos, aren't they? Jalapeno, get my pronunciation right. Not as hard as the previous one. What do you guys think about trig substitution as a strategy for solving tricky integrals? This is our last day talking about it, so it's kind of interesting. Yeah. As far as integration strategies go, it is probably the beefiest of all the different integration strategies. It's long. Yeah, it's long. I think it's kind of beautiful though, it's just the power of trigonometry is kind of cool. I love how you do some trigonometry and then it goes back and it ends up as algebraic in the end, like this one, it's like, where did all that trigonometry come from? Well, some creative mind. I don't know who invented this idea, but yeah, I think there's I think it's a little more formulaic. It's long, but it's a little more like it's clear what to do at each step, because it's like you do this and then you do that and then you do that, and there's not as much guess and check as there is when you're doing the trig integrals. Trig integrals is like, wow, well, I could use integration by parts, or I could make a replacement with a trig identity, or I could try u substitution, and it's just like, wow, what am I going to do? You got to just kind of, practice and figure it out. But yeah, trig sub's not that bad. Folks, have a great weekend. Next week, we're going to carry on with some other advanced integration techniques. The one we're going to do next is going to use polynomial long division. So if you want to go back and review another thing from pre-calculus, go and look at polynomial long division. And that'll help you a little bit on Monday. Okay. Thanks, everyone. Great weekend.